Section 5.4 in the textbook is about the indefinite integral and the net change theorem, but for this video we'll just be talking about the indefinite integral. So here's the definition. We write it this way. This is the integral of f of x dx equals, it is the family of all antiderivatives of f of x. So for instance here, if I write this, then this means take the family of all antiderivatives of this thing. So this being a sum, I know that I can just do each piece individually. So the x squared turns into an x cubed over 3, the antiderivative of cosine x is sine x, and then I just add a plus c to describe all of them. Okay. In section 4.9, when we were talking about antiderivatives, we didn't really introduce a notation of this symbol means take the antiderivative. Well, now we are. This integral symbol dx means take the antiderivative with respect to x. I should point out that it is important for several reasons as we move through this course that you remember to include your dx. It's like when you're taking derivatives in Calc 1, you need to know what the independent variable is so you know whether you're applying a chain rule or not. And likewise here, the dx is an indication of what the independent variable is as you're taking your antiderivative. Okay. Now notice here that the notation for the indefinite integral is very similar to the notation to the definite integral, but the result is very different, because if I had the definite integral of f of x dx from a to b, so this would be the integral from a to b of f of x dx, this is equal to some number, right? It's the area underneath this curve, and I don't know if you can see me, but I'm quoting with my finger, doing air quotes, saying under the graph, because if the function is negative, then of course it's the negative area over, but anyway, this is defined in section 5.2. The definite integral, the result is a number. On the other hand, the indefinite integral of f of x dx is a family of functions. They are related because we saw with the fundamental theorem of calculus that in order to calculate the area underneath a function f, it can be done by finding an antiderivative, plugging in the endpoints, and subtract. So this integral sign, although we first think of it in terms of calculating area, it is very closely related to antiderivatives, and we cement that relationship by using just that symbol itself, not from a to b, but just this integral symbol with a dx to signify find the family of antiderivatives of this function f. Okay. If you flip to page 398 in your textbook, you'll see this table of indefinite integrals. It's essentially all of the derivative rules that we learned from Calc 1 turned around into antiderivative rules. Now, not quite all of them, it's all of the ones that are easily turned around. So, the first two here, in Calc 1, it was the derivative of a constant times the function is the constant times the derivative, and now it goes the other way. The antiderivative of a constant times the function is the constant times the antiderivative of the function. Likewise, in Calc 1, the derivative of a sum was the sum of the derivatives, so now the antiderivative of a sum of two functions is the sum of the two antiderivatives. Okay. Now, those two properties, I should point out, there's various things that we'll run into in our mathematical travels here that satisfy properties like these. Essentially, this operation of anti-differentiating commutes with multiplying by scalars, and it looks like it distributes over addition of these things. So you've got a sum of two functions with this operator applied, and the result is the sum of the operators applied to the individual pieces. Right? Those two properties together make this operator what's called a linear operator. Should you find yourself interested in linear things, I would suggest you take a class called linear algebra. Anyway, and then there's a bunch of these derivative rules. I mean, we know that the derivative of e to the x is e to the x, so the antiderivative of e to the x, or the indefinite integral of e to the x, is e to the x plus a constant. The derivative of the arctangent of x is 1 over 1 plus x squared. So the antiderivative, or the indefinite integral of 1 over 1 plus x squared dx, is the arctangent of x plus a constant. So all these rules are derivative rules that you learned in Calc 1, and now we're just rewriting them as antiderivative rules. Okay. One thing I want to point out here is that when we do a problem like this one here, where I'm going to say what's the integral of 1 over x squared dx, well, I think of that as the integral of x to the negative 2 power, and I'm using the power rule, so that would be x to the negative 1 power divided by negative 1 plus c, so this is minus 1 over x plus a constant. There's an unstated assumption here that I'm going to state, in that this function is not a continuous function to start with, right? 1 over x squared looks like this. There's an asymptote at x equals 0. And when you take this antiderivative, you get minus 1 over x, which looks like this, or any shifting of it. You can take that 1 over x and shift it up or down. But actually, it's slightly more complicated than that, in that on each of the intervals for which this was continuous, so from 0 to infinity, or from minus infinity up to 0, you can shift each piece however you want, up or down. So the general antiderivative isn't really just this, because you can take each piece and say shift this piece up like that. It should be a little more curved, and shift this piece down like this. The thing is, still, if I look at the derivative at any point here, this has, positive but very small slopes getting to be positive very big slopes, like that does, and over here it's still positive big slopes coming down to positive small slopes, just like positive big coming down to positive small. So this is still the antiderivative of something like this down here, but it's not just this graph shifted all by the same amount. When you have functions that are discontinuous, you can do the shifting within each of the intervals of continuity. So, for instance, the example that I did above here with the x squared plus cosine x squared is polynomial. It's continuous everywhere from minus infinity to plus infinity. Likewise, cosine of x is continuous everywhere from minus infinity to plus infinity. So this has just one interval where it's continuous, all the way from minus infinity to plus infinity. So there really only is just one c. All the antiderivatives of this function are just this function shifted up or down by adding different constants. Okay. But as soon as you get that function with an asymptote or a break in the graph or something, then the antiderivative is a little more complicated than just this, because you can shift each piece individually.